The problem about using the mole as a measurement in chemistry is that it's impossible for most people to visualize because we can't actually visualize how many grams of salt, for example, are in 1 mole. Well, the good news is that you no longer have to. Today we're going to be talking about a variation on moles that we call molar mass, which simply is a ratio of the number of grams of any given substance that exist within 1 mole of that substance. Now, we can use our periodic table in order to find out what this number is for every single element. So, for example, in our first question, we're going to be looking at sodium chloride. Now, if we look on the periodic table, we see that the atomic mass of sodium is 22.99. And if we go over to chlorine, we see that the atomic mass of chlorine is 35.45. Now, up until this point, you haven't actually learned about what the units are for atomic mass other than in the context of protons and neutrons. The other way that we can use atomic mass is in the form of molar mass. So in order to find the number of grams per 1 mole of every substance, all you need to do is look on the periodic table and find the atomic mass of that substance, and from there, solving molar mass problems is a relatively simple unit conversion problem. For example, if we find out that we have 6.75 grams of sodium chloride in this tablespoon here, and we want to know how many moles of NaCl we have all of the information that we need. So if you recall from the periodic table, the molar mass of sodium is 22.99 grams per mole, and the molar mass of chlorine is 35.45 grams per mole. If we do a quick add of these together, we find that the overall molar mass, the overall number of grams per mole of sodium chloride is 58.44 grams per mole. Now, the unit that we want to cancel is grams, and the unit that we want is moles. That means for our conversion factor, 1 mole goes on the top, and the number of grams per 1 mole of sodium chloride, 58.44 grams per 1 mole, goes in the denominator. We see that grams is in the numerator and the denominator, so it cancels out. And if you put this into your calculator, you will find that this comes to approximately 0.116 moles of sodium chloride. And again, the reason why we rounded this to 3 decimal places, or 3 significant digits, is because our starting measurement, 6.75 grams, is also in 3 significant digits. So in short, this is the simplest possible calculation that you can be given for molar mass. But what about more complicated situations? So let's say we're dealing with a measurement that you don't normally associate with mass. Let's say that we don't want to weigh this bottle of water, but we know that there are exactly 500 milliliters of water in this bottle of water. So this time we're starting with 500 milliliters of H2O. Now, because this measurement is not in grams, we can't actually use this measurement directly with the molar mass. However, if we know another unit conversion here, a conversion that will allow us to find out the mass of water if we know how much 1 milliliter of water weighs, we can find out the exact mass of 500 milliliters of water. In this case, we know that the density, which we represent with the Greek letter rho here, of 1 milliliter of water is equal to 0.997 grams per 1 milliliter. We see that milliliters cancel out like this, and here, if we do this, we would have calculated the mass of 500 milliliters of water. But again, that's not what the question asked. Here, we're actually asked how many hydrogen atoms we have. Now, in order to do that, we need to convert grams into moles, and then we can use Avogadro's constant, 6.02 times 10 to the 23, to find out the number of atoms that we have. So let's convert to moles. Now we want to get rid of grams and we want to replace it with moles. So let's find out what the molar mass of hydrogen and oxygen are on our periodic table. We see the molar mass of hydrogen is 1.01 grams per mole, and the molar mass of oxygen is 16.00 grams per mole. Let's add the two together. Remember that you've got two hydrogens, so 2 times 1.01 is very simply 2.02. Molar mass of one oxygen is 16 grams per mole. Do some quick arithmetic here, and we find that the molar mass of water is 18.02 grams per mole. Grams cancel, and so we found out the number of moles of water that we have in 500 milliliters, but again, we want to know the number of hydrogen atoms. So firstly, we know that there are 2 hydrogen atoms per every 1 water molecule, because it says right there in the formula. We see water in both the numerator and the denominator, so it cancels. And now we know the amount of moles of hydrogen atoms, but again, we're looking for the individual number here. So we remember Avogadro's constant. 1 mole is equal to 6.02 times 10 to the 23. And in this case, we're looking for H atoms, so moles cancel. And from there, that tells us that because hydrogen and atoms are the only 2 units that remain, if we put this into our calculator, that will tell us the number of hydrogen atoms. If you go ahead and do that, you will find that this number comes to approximately 3 times 10 to the exponent 25 hydrogen atoms. And again, we've rounded this to 1 significant digit because there's no decimal place here. Both of these numbers here are 0, so they're treated as not being significant. So the only significant digit at the beginning is the 5. So 1 sig fig here, and that mirrors our final number. Finally, we can talk about going the other way. Let's say that we know how many moles of copper 2 sulfate pentahydrate we have in this pile here, and we want to predict how many grams this mass or this sample would actually weigh. So let's set up our problem first. 0.987 moles of CuSO4 with 5 water molecules associated with it. Here, in order to find the molar mass, this is going to be fairly complicated because we have a large number of atoms here. So let's go and look up the molar mass numbers that we do not know, which are copper and sulfur. So here's copper. Copper is 63.55 grams per mole, and sulfur is 32.07 grams per mole. So let's get those written down. 63.55 is copper, and 32.07 is sulfur. Now, we need to take note that we have 4 oxygen in copper 2 sulfate, and we also have 5 water molecules in the waters that are associated with it. We know that the molar mass of oxygen is 16. If we multiply 16 times 4, this comes out to 64 grams per mole. So let's put that in there. And through some calculator wizardry that we preempted, 18.02 is the molar mass of water, which we calculated in the previous question. And if we multiply this by 5, this comes out to exactly 90.10 grams per mole. And if we do some quick arithmetic here, make sure that you do this. You don't need a calculator to do this as long as you are careful with the arithmetic. And this should come out to, If you did the arithmetic correctly, this should come out to 249.72 grams per mole. So if we want to know how many grams we would have, we need to eliminate moles and convert to grams. So here, moles would go in the denominator, and we would put our molar mass that we calculated in the previous step in the numerator. Moles cancel, leaving us with grams. And if you input this into your calculator, this comes to approximately 246 grams of copper 2 sulfate pentahydrate. Again, we left our final answer at 3 significant digits because our initial measurement only had 3 significant digits. Assuming that's done, that's how we do this. So what we have shown here is how to use the atomic masses, which we now know are in the units grams per mole, on the periodic table in order to either figure out how many moles of a given substance are in a known mass quantity, or if we know the initial number of moles of that substance, how we can use the molar mass in order to find out how many grams a certain number of moles weighs. And again, with our second example, how we can do variations of that, both involving Avogadro's constant and involving other less common conversion factors. In the next video, we're going to look at how to calculate the number of moles and mass based on substances that we don't typically associate with being able to find their mass.